Hi, and welcome to the third video in a series about analysis 2. In the first two videos, we looked at some important topological properties of the real numbers and how they naturally generalize to r to the n, and we looked at the review of metric spaces and distance functions, of certain kinds of distance functions that we can induce on r to the n, that is the Euclidean supremum norms. We looked at open and closed sets, and we looked at limit points, and in our second video, we saw how this treatment of compactness and of connected spaces really works in a general sense. So we reviewed that from analysis maybe the first time, and those suitably generalized to r to the n by just letting whatever arbitrary metric space we define there, or topological space, just setting those to r to the n. Specific cases, we saw some results like the extreme value theorem and the intermediate value theorem for compactness and connectedness, respectively. So with those in mind, we would like to turn our attention to an extremely important topic, which is going to be that of differentiation in r to the n, and this is going to require a bit more of a perspective shift than maybe some of the more easily generalizable ideas of topology in the real numbers to r to the n. So we want to develop a suitable notion of what it means to take the derivative of a multivariable function, of something that really captures what we want about the derivative, while keeping its core properties in mind, what we want out of it, and kind of iterating through, as we'll see, kind of first definitions or how we might think it behaves, and then eventually landing on a suitable definition for our generalized derivative. So to do this first, we're going to just take a very quick review of differentiation in R1, that is from maps from R1 to R1, so just the lowest dimension for both domain and codomain, which is what we study typically in calculus or analysis 1, where we take I in R to be some open interval on the real line, and you define this function that you want to differentiate from I to R. We take some point in our open interval, and we define the derivative of f at this point. So we define our derivative, and we notate it when in R1 f prime of a, and this is equal to, as we take t to be some value that goes to 0 arbitrarily small, we take that limit and we define this quotient. So f of a plus t as t goes really small, minus f of a at the point, all evaluated divided by t. So this is our idea of the derivative of f at a. And really our motivation for this video is going to be settling on how we can regard this in transformations from, let's say, r to the n to r to the m, or something like that, where we want general definitions of differentiation for multivariable functions. And one thing that you might have seen in multivariable calculus at first is this notion of the directional derivative. And at first, this seems like quite a natural generalization of the derivative, but as we will see, it doesn't quite satisfy all the properties that we want out of differentiation. But we will go over it anyway because it is important because of how it helps us think of partial derivatives, for example. And to motivate the directional derivative, we will kind of consider letting sort of analogous case here, u to be an open set in r to the n, and we take some function from this open set u in r to the n to r to the m. So we've got this linear map, I haven't really specified linear yet, but we'll see it's going to be, that's how I'll think of it. So we have this map from u in r to the n to r to the m, and we take some point in our domain as we did in one dimension, and we want to define this idea of directional derivative with respect to some vector u. So we're given a vector, and we want to find the derivative in that component or direction, basically. And our directional derivative, f in the direction of u at a point a, is going to be notated, first of all, big D sub u, f of a, and this is the differentiation operator. The subscript just means that it's in this direction, so this is going to give us the information. F is our function, a is our point. So this is defined as, and it looks very similar to how we put it here on purpose, the limit as some t goes to 0, where we take f of a plus t times u minus f of a over t. And this looks very similar, but it differs because now we're multiplying by this given u, whereas we didn't have to here. But notice now that our point a is going to be in our domain r to the n, so it's going to be some sort of n-dimensional entity that we have to refer to. So oftentimes we just write points in r to the n as column vectors, so of n components. Hence we have our direction u, whereas we didn't need to specify that in just one dimension. And this is going to be the derivative in a given directional vector u. So this is interesting because we can take these like suitable choices of u, so ones that give us the most amount of information, or ones that kind of break up our function or our study of a function into really its constituent parts via its so-called partial derivatives, which might be a familiar idea, but we'll just codify it here. So we can take directional derivatives by setting our directional vectors as the standard basis vectors of r to the n, where recall that our standard basis is going to be some, notated first of all, e sub 1 through e sub n. And each of these is going to just give you, for e sub I, you have a 1 in its ith slot and then zeros everywhere else. So this is a orthonormal basis, that is, every vector has inner product. You take them and they're all orthogonal to one another, basically. So just from a loose point of view, strictly speaking, they make right angles with one another. Their inner product gives you 0. And you have all of them to be normalized. So if you take basically their norm, they're all going to give you 1. So this is our standard basis, so-called, of r to the n. Just a quick recap of that. And this is going to give us a lot of information about our function in particular when we take its directional derivatives with respect to these vectors, because it really tells us how we can break up our function into its constituent parts. That is, how it behaves with respect to each of these basis vectors, or how it tends in each of those. And we have special notation, in fact, for taking a directional derivative with respect to a standard basis vector. If we're looking along a certain component, let's say if you have in just 2 dimensions your x and y axes, and you look at your standard basis vectors, like in the x direction and the y direction, it's kind of like just breaking it up into the components of how it behaves with respect to one direction versus the other, and differentiating just based on its directional derivative at each. So we have this differentiation operator at e sub I applied to f of a, and this is our partial derivative with respect to x sub I f of a, right? So this is going to be our definition of a partial derivative, right? Now, with this in mind, we want to ask ourselves, first of all, is this a suitable notion that we can employ to ensure differentiation and hold the same kind of properties that we did for just one dimension? The answer turns out to be, if we just say, over here, we just put this question, how do we generalize differentiation to n dimensions? If we just try to say, well, if all of these partial derivatives exist at a point, we run into some trouble. And let's look at some counterexamples as to why. In fact, that is not even the strongest requirement that turns out to be false. There's something even stronger than requiring the basis vectors to exist at every, these partial derivatives to exist at every point for it to be differentiable in the sense that we want it to be. So here's our guess 1. We're going to run through some kind of guesses or ideas to throw out, and we'll go along and explain why. For example, if we have these partial derivatives exist, that is, for each basis vector, you're taking your directional derivative with respect to those. At some function f of a, we want to know whether these all existing at your point for a function is going to ensure the fact that it is sort of, putting air quotes around this, differentiable now, because we haven't exactly defined that yet. So we consider this function, and oftentimes in analysis, or I know especially when going through Rudin's book for the first time, it was these kind of counterexamples that seem to come out of thin air, but hopefully you'll see why the construction of this function, and in fact its generalization, is almost directly intended to counteract why this proposition seems to work at first. So it doesn't actually. We consider this function on x1 and x2, so of 2 variables. We might just say x and y, but I'm trying to keep it with this notation here because that's really the most general form. So we have f of x1, x2, and we define it to be as follows. We have kind of this discrete valuation here where we have 0 if either x1 or x2 is 0. That is, if this point is either on the x1 or the x2 axis, and we define it to be 1 otherwise. So first of all, we already might have like a loose sense in mind that this is not differentiable. This is not something we can take the derivative of in a certain way, and it turns out only to be in specific cases that we can really establish that this is just differentiable along certain paths, but for everything else it won't be. This is because the ones that do exist are going to be along the paths of these basis vectors, right? So if you take the partial derivatives with respect to x1 and x2, at the origin you get 0 for both. And I just wrote out here y kind of more explicitly. So for I from 1 and 2, we just have 2 dimensions here, but we can just as easily have I run from 1 through n. You take the partial derivative at 0, 0, which is just the limit as t approaches 0 of f of, this should be the 0 vector, as it is over here, 0 plus t times e sub I, because e sub I is where we're evaluating, minus f of t all divided by t, right? And we know now that if it approaches along x1 or x2, so if it evaluates like this, then this just goes to 0. So we have our limit as t approaches 0, f of t times e to the e sub I, minus f of t, all divided by t, so this is just going to go to 0. We have our partial derivatives now that are defined for this point. But we want to show, in fact, that it is not a differentiable function overall. And this is to show that f is not differentiable specifically at the point that we showed it is partially differentiable at. So the partial derivatives existing for a function, we want to show that doesn't necessarily imply that it is totally differentiable. And we state that because of this now, I hadn't written this part out explicitly because I'd intended to kind of give more of an intuitive understanding of why. Basically, this is kind of a jump, and you'll see that it's not even continuous, really, because if you approach along any other path other than these basis vectors 1, 0, and 0, 1, you are going to get a derivative that is not defined. So if you approach along any other path, this is not going to give you, this is not differentiable. So you can check this for yourself, and in fact, those are the only two cases in which you do have differentiability, or kind of a very, very rigid idea of it being differentiable in just those two contexts. So this is not a differentiable function, hence we've shown our first kind of guess to not be as broad as we'd like it to be. Our second guess now deals with a more general case than supposing the partial derivatives exist. Instead of all partial derivatives existing, we say, is it possible to show that we have a suitable definition of differentiability if we ensure that all directional derivatives exist at A? And this is different from the previous definition because while we have all partial derivatives, that is, directional derivatives strictly with respect to standard basis vectors, in this case we're showing that for any given vector u in our domain, we want to look at the case where all of these directional derivatives exist, not just for standard basis vectors. So we're going to explore this case, and actually the construction of a counterexample is going to be a little less intuitive than it was before, because before it was almost by construction that we wanted something that behaved nicely only along the paths that that kind of fit our condition of exploring these paths along standard basis vectors. But now in general, we want to look at something that is not defined, that is not going to give us, our differentiability requirement just based on this. So we're just going to state the counterexample and kind of check why it doesn't work. And our counterexample, is going to be given by some function f, which is going to map from R2 to R. So it's two-dimensional in the domain and one-dimensional codomain. And I'm going to write as x and y here because if I tried writing this with subscripts x1 and x2, and it got incredibly confusing with all the superscripts and all the notation going on. So this is just familiar as a function of x and y. And we define it again in this kind of discrete way as we did before, where we define if we're not at the origin, that is, if x and y are not both 0, you take this to be xy squared over x squared plus y to the fourth. However, if it is at the origin, then we have 0, so x equals y equals 0, and we want to show that this is in fact not a differentiable function. Here is our claim. So we claim that, first of all, what we want to check is that this satisfies our requirements for our guess. So this is a function where all of its directional derivatives exist, for example, at our point 0. So 0 is taken to be 0, 0. Of course, x and y are both 0. and we want to show that all of these directional derivatives exist. So we take u to be arbitrary. That is, we take u to be equal to some point a, b, which I denoted by this column vector. And then we have, just by our limit definition now, we take our limit because since we're at the point 0, we just have the 0 plus t sub u. So sorry, 0 plus t times u, which is just going to be t times u. So f of this minus f of 0, 0, which is our point, all divided by t as t goes to 0. Evaluating this a bit more, we just get this to be f of t u, and we get f of t u over t as t goes to 0. Now just directly evaluating f on t times u, we get u at, u of course equals this column vector at this point, and you can check that it actually expands to this. So as t goes to 0, we just plug these in and we get t cubed ab squared over t squared a squared plus t to the fourth b to the fourth. And I pulled out this t here as just times 1 over t at the end. This is all supposed to be within the limit though. And just kind of canceling out a factor of t squared here first, we take t times ab squared over ab plus t squared b to the fourth. This is times 1 over t, and this evaluates now canceling this final factor of t from the numerator. We have the limit as t approaches 0 of ab squared over a squared plus t squared b to the fourth. Now, there are two cases that we have to look at here, and these have to do with the value of a at certain points. So, first of all, if we have the fact that a does equal 0, then this whole thing just goes to 0 itself, right? Without any supposition on t yet, so we just know that this numerator is 0. If a squared is 0, then we have t going to 0 for some, so just 0 over this, and this just goes to 0 itself, right? But if a is non-zero, which is, in a sense, the more likely or general case, a is non-zero, then we just evaluate t going to 0 here. So this term over here evaluates to 0 as we take the limit, and we are left with ab squared over a squared. Now just canceling our factor of a, we get b squared over a squared divided by a, so b squared over a for a non-zero. Hence, we have shown that regardless of our choice now, of any point, the directional derivative is going to exist. So at 0, 0, in these two cases, all of our directional derivatives exist for our function f. So that is our first kind of supposition, and now we really want to show our contradiction. So what's the kicker here? The kicker is that f is in fact discontinuous at the origin. And just stop for a second and think about why, and it's really just in the definition, right? So it's discontinuous at the origin. Just look at this function for a moment. If we take x equals y equals 0, this is not defined. So we don't even have a continuous function, but we have the fact that all of its directional derivatives exist. Hence, if the existence of all of these directional derivatives at a point doesn't even ensure continuity at that point, this is not really a useful formulation of differentiation the way it was in R1. So we kind of have to go back to the drawing board again and think about why, like what we might want now. And we've gone through this kind of nasty counterexample, and now we will think of our guess, which I'm already kind of giving away as how we want to think about it. So this is going to end up being correct. And this is going to solidify the notion of the derivative as a linear transformation. And linear transformations, as you'll recall from linear algebra, have associated matrices that we're going to work with, and we're going to end this video probably with a very important matrix that has to do with partial derivatives. So for guess 3, and I'll just start writing here because I'd already written the parts above, and I felt like I should just write the most important part while recording. Let's just recall from single variable analysis, we defined f prime at a, so f is kind of implicitly, as I said here, from R1 to R1. This is just our limit as t, sorry about that, t goes to 0, f of a plus this discrepancy t minus f of a, and we divide this all by t. This is our derivative for f from some interval which is open to r, and then a which is in our interval here. So now we consider a function based off of this. So consider what we'll call lambda here, which we define from the real numbers to the real numbers, defined by, we have lambda t is going to equal our f prime of a times t. So this is certainly a mapping from R to R, and this is how we're going to look at lambda. So why is this a useful formulation? We will see in a moment. So turns out now, with our definition here, we can really just pull out this f prime of a and subtract it from this left-hand side. So the limit as t approaches 0 of f of a plus t minus f of a minus lambda of t, all of this over, that is an atrocious fraction bar, I'm sorry. All of this over t is going to equal the limit as t approaches 0 of, now define, remember how we define, lambda to be f prime of a times t, so we can just divide out by t, and we get this formulation of f prime of a equals lambda of t over t, which we see over here. So f a plus t minus f of a, we take this to be over t, and we have minus f prime of a. And this is going to equal 0, right? This makes sense. And we note the role of this lambda here, where lambda of t kind of approximates, roughly speaking, f of a plus t minus f of a when t goes to 0. So as t becomes extremely small, arbitrarily small, then we note that this lambda resembles f of a plus t minus f of a. And I think now we will be ready for our idea of generalization to n dimensions. Sorry about that. So generalize to n dimensions. Let U be an open set in R to the n. We take U to be our mapping from U in R to the n to some R to the m, and we take A, as we have been doing before, to be a point in our open set. So f is differentiable at A if there exists a linear map this is what I had alluded to kind of preemptively earlier, which we will call B for now and kind of adjust our notation later as we see fit. Our mapping, which carries the same way as our function does from R to the n to R to the m, such that for all h, we'll say, h is going to play the similar role to t, so Rn minus, let's say, 0. Another notation I might use for this is Rn star, but that's kind of confusing because we already have a superscript. So all non-zero vectors in R to the n, we want this formulation to hold. So f of a plus h, where now h is going to play the similar role to t. Instead of t now being a real number, we want h to, of course, be our notion of distance in n dimensions, so we want it to be an n-dimensional vector as we defined here, non-zero. So f of a plus h minus f of a, familiar, minus b applied to h, b times h, so we have our transformation here times h. And all of this we take the quotient over now. It's kind of meaningless to divide by h as it is here because that's just dividing by our vector. So we want to take our distance, which is going to be our h, that discrepancy value to be as arbitrarily small as we would like. And to just get our distance of a vector, we can do the absolute value of the vector here. So this is our notation in the sup metric, and we can just as easily have put the double bars because we know that there's an equivalence between Euclidean and the supremum norms as we saw earlier. So this approaches 0 as h approaches 0, i.e., and this is just something I want to add, although I sort of pointed it out, f of a plus h minus f of a, this is going to be similar to how we took this discrepancy value in one dimension as we define this lambda of t over here. So now instead of lambda, which is just a one-dimensional linear transformation here, we want a linear transformation which is suitable, that is b times h as h approaches 0, right? Or when h is very small. So we have kind of generalized our notion of the derivative as a linear map now, where we looked at the derivative in one dimension as just a one-by-one linear map. That is, we can just take a single value, but now it's going to be more general, where we have b to be a linear transformation from r to the n to r to the m. And we know now from our knowledge of linear algebra that this kind of linear transformation is going to have an associated matrix. So there's a one-to-one correspondence between linear maps and matrices. And with respect to the dimensions of our domain and codomain, we know that if, in this case, our domain has dimension n and our codomain has dimension m, we are going to get B to be an m by n matrix. I'll expand on this in a bit. And here's our theorem to really solidify why this formulation of differentiation is actually the right one. It has this strong corollary that if f is differentiable at a, then for all u in, let's say, r to the n, as we've been doing, then du f of a, that is the directional derivative at our point a with respect to the vector u, exists. So this is powerful because differentiability implies existence of all directional derivatives, but not vice versa, as we saw with our counterexample earlier. So this converse does not necessarily have to hold true, but we'll see and prove that the forward statement does. So proof. How do we want to go about this? We take the limit as t goes to 0 of f of a plus t times u is the direction, minus f of a minus b of t sub u. Sorry, not sub u. I don't know why I've said that twice now. So bt times u as vectors. And now, in replacement with our h here, we're just taking h, since h can go very small, as the product of t times u. So this is perfectly valid as far as our formulation of differentiability goes. So this equals 0. Sorry, I forgot to include that in. So this is our just definition up here we're reiterating. And this limit is going to be evaluated as follows. And it follows now also that, just analyzing our term over here, f of a plus t times u minus f of a minus b of t u, all of this over, oh, that's not quite right. All of this over tu, and we just set up some logical equations that follow here. T over t times u, and we multiply by top and bottom. So t over tu, and we just take f of a plus tu minus f of a. I'll just curl up for greater clarity here. B of t times u. And now, since we've kind of brought out this factor of t, we want to divide the numerator by t, because that's just an equivalent expression. So we are happy with this, and we're perfectly fine. And now we can split up our absolute value here, as a matter of fact, where now we can take First of all, this linear transformation being linear, t being able to be pulled out of this because you're not applying it to t times u, t is going to be a scalar with respect to this linear transformation. Hence, by the property of homogeneity of linear maps, you can pull out this t as a scalar and cancel as we will in 2 steps, actually. So first we'll do t over absolute value t times 1 over absolute value u. And I should really say not absolute value, that's kind of force of habit, but it's just the norm, f of a plus t times u minus f of a, all of this over t, and now we just pull out this minus t, minus t times b applied to u. I'll just do this notation so it's unambiguous, and this is over t, so we're just splitting up this difference like that. T over norm of t, 1 over norm of u, times, this all is fine, and it's familiar, as we'll see, a plus t u minus f of a, all of this over t, and now we have minus b applied to u. Okay. Taking this limit, so I'll just write this in words because I don't want to rewrite this whole term, actually. As t goes to 0, what do we notice? We notice now that as t goes to 0, this all goes to 0 as well, right? By supposed. So if this all goes to 0, as t approaches 0, f of a plus t times, a plus t times u minus f of a, all this over t, is going to approach b times u. Okay, so now we have shown this, and it's just worth noting that this linear map is going to be unique, so it's a well-defined definition or formulation that we've supposed here. So we're done now with that. And we are really going to define now the derivative of a multivariable function. I know it's taken like half an hour of time, but hopefully this has been a clear exposition of that. And we're going to do this, go through a few more facts about differentiability, and conclude at the very important matrix that I was referring to earlier. So the derivative, or rather this motivates the definition that the derivative of f at a point A is going to be written just generally. This differentiation operator without any subscript indicates that it's the general derivative. D applied to f of A, which equals b, and b is from r to, let's say, r to the n, r to the m, which is defined above. So this is our linear transformation. It is really how we can think of this mapping b here to be our derivative, just as we thought of our lambda, the role of our lambda here, so our f prime of a being, lambda of t being f prime of a times t. Similarly, we can think of the derivative itself being the information that we receive from our matrix or linear mapping b. This is an equivalent formulation from one dimension, and it is in fact a suitable generalization, as we saw. So just as kind of worth noting because of this, even though it's totally tautological by both these definitions here, this is a linear map. Linear, i.e., sometimes you'll see this notation, so L, r to the n, r to the m. This is just this just means the set of all linear maps from Rn to Rm. It's a good shorthand to have. Now we want to verify our key property, which our two suppositions of differentiability failed us earlier with, and that is the fact that differentiability implies continuity. And it turns out now, due to this theorem, let me write this out fully. Differentiability implies continuity. Why is this the case? So, proof. So, the statement that f of a plus h minus f of a minus, we'll just keep our notation b, rather than writing out the full differentiation matrix there. So we just copy our definition here, going to 0 as h goes to 0 implies now that our numerator goes to 0 as h goes to 0. So f of a plus h minus f of a minus b times h goes to 0 just as h approaches 0. And it just directly follows from this now, our limit definition, that hence f is continuous. Okay, so that's a conclusion. And now we're going to really look at more of this idea of derivative of as a linear map. So, let T, and first of all, we just take a survey of linear maps from, say, Rn to Rm. So let this be linear. Take a point, any point A in Rn. Then, by virtue of our standard basis, or for that matter, any basis, but for convenience, we just want to write this in terms of a linear combination of scalars and basis vectors. A is equal to the sum across I equals, let's say j equals 1 to n, a sub j, e sub j. So what this means is you've got some scalars, a sub j, which are those scalars such that you can express any vector as a linear combination of those and the basis vectors. So this is going to be just a1 through an, right? So then we can apply t to this point where t is going to be applied to this sum. So, sorry, I just can't get my sigmas right sometimes. So j equals 1 to n, and we take a sub j. Of course, we can pull these out of the linear transformation as needed, and we apply t to e sub j, right? T can be written out itself as components, and this is a little bit of a abusive notation, I think, but hopefully it's clear that I mean now these are kind of going to represent the rows. So you're breaking up your linear transformation into the, sorry, I meant columns. So where each t sub j from Rn to R for each component now. So together you can regard this as Rn to R, but really you're just thinking of this now as just kind of individuating your codomain. You're looking at the way that each component of T projects onto a respective copy of the real numbers for all of those real number copies in R to the m, basically. So you have this is a linear map. Let's just say linear. Then we can write this in a form such that now applied to each of these e sub j's, we can write this as t1 ej, so on and so forth, till tm ej. And we have that t sub I applied to E sub j is going to equal to, let's say, some, I shouldn't use A again, but maybe the notation they use in these notes is little l. That corresponds with this big L, which they use for linear transformation. I'm used to using t. So let's just say little t. T I sub j. So this forms a representation as a n by n matrix. I really stumbled on those for a second. This forms an n by n matrix written sometimes just with respect to its entries, which are defined j. Okay, so this is kind of more of a linear algebra perspective. Here is a remark that we might have. If we let u to be in r to the n, open, and we take these component functions f1 from Rn into what we'll just write as Rm1. And we have f2 Rn into Rm2 so we have our transformations as follows. Differentiable maps. So we have this supposition. We let m equals m1 plus m2 if r m sub 1 times r m sub 2. Remember, now taking Cartesian products of these vector spaces, you just add their dimension. We let this be Rm, or at least isomorphic to it, but that's a moot point anyway. Construct a function based on these constituent ones. So we construct a function f from Rn to Rm by, sorry about that, f, kind of in this component or parameterized form, equals f sub 1 comma f sub 2. Then we take the derivative of f of a, at a is more precise, and we take this derivative and see that taking this is going to just be differentiating at each coordinate. So d f sub 1 of a, d f sub 2 of a, right? And this is going to be our just notion of splitting up a function or differentiable function into differentiable parts or vice versa. So that's going to also build a foundation for what we want right now. Remark. So we let u be again this acting subset of r to the n, and we want f from Rn to Rm. So then we have f of some n-dimensional vector x. We can split it into these components. The action of f on x is going to carry into Rm, and so we can just kind of, as we saw above, look at it as m different functions of acting on x, right? So f sub 1 through f sub m of x. Hence, we can think of this map as f equals this tuple of components, f1 through fm. Each f sub I, as we saw earlier, is going to take from the open set u, or r to the n, whatever your domain is, and it's going to map into each copy of r, right? So for however many I there are indexed from 1 through n, through m, and you're going to map into the real numbers. So for each one, this is going to be just a linear functional, if you're familiar with that term. So now we examine the specific case where we are taking the derivative with respect to acting on, let's say, the standard basis vectors. And we just kind of explored that by writing it like this. And to do this, we notice that, first of all, we've broken up our function, so we can just write df1 of a, e sub j, so on and so forth, till df m of a, e sub j. And just by our notation earlier, by this action on the basis vectors, we find that this is in fact the partial derivatives of the components of f at these xj's of a. So on and so forth till dfm with respect to x sub j of a. And this is going to be a representation for that. Hence, df of a can be represented as this m by n matrix, as we saw earlier, or not quite like this, represented as an m by n matrix. And we have this, basically this relation here now, where we've taken this differentiation operator at the point a of f, and we set this equal to j sub f at a, which is going to be the m by n matrix delta sub f sub I with respect to del x sub j at a. This is called the Jacobian matrix. This is that important matrix. So it is the matrix containing all the information of the partial derivatives, and this is an equivalent formulation of all the information we need to know the differentiation operator acting on some multivariable function f. So this is the Jacobian, named after the great mathematician Carl Gustav Jacobi, and it is called the Jacobian matrix. This is the Jacobian of f. Again, I'll specify this just to make clear this whole dimension thing that's going on of the matrix and the transformation at a. Right, so I can just make a little note here. This is m by n. Okay, and really this is the culmination of what we wanted to show through our idea of differentiability at first, how we might have proposed it, and eventually landing on this idea of the Jacobian matrix as the analog in multiple dimensions of the regular derivative, or one-dimensional derivative, as we are familiar with. So that will conclude probably this part, and in the next video we're going to look at some conditions for differentiability. That is, we looked at some conditions where sometimes it's not sufficient to conclude, in fact, we don't have enough information to say that a function is differentiable. For example, the existence of all of the partial derivatives at a point, or all of the stronger condition that all of the directional derivatives in general at a point, neither of those ensure differentiability. But now, equipped with this formulation of differentiability as kind of this Jacobian matrix here, we want to impose some condition on these partials so that we have a continuous function at a point. And that's what we'll look at. So thank you for watching this, and I hope to see you in the next video.